everybody, Avery the Applications Astronaut talking to you about concavity and the second derivative test. Another question for you, what happened to the astronaut when he dropped a rocket on his foot? He got mistletoe.
First thing we're talking about is concave upward. So given differentiable function f on interval I, the graph of f is concave upward on I when f prime is increasing, or the second derivative f double prime of x is greater than 0 on the given interval. When we're talking about concave downward, given differentiable function f on interval I, the graph of f is concave downward on I when f prime is decreasing, or f double prime is less than 0 on that given interval. So let's break this down. A graph is concave upward when f prime is increasing, or the second derivative f double prime is positive. So just like we know a function f is increasing if f prime is positive, we know that f prime is increasing if f double prime is positive. So if our second derivative is positive, then f prime is increasing. Now what does that mean? Well, f prime, remember, is the derivative of our function. It's the slopes of the tangent line to the curve. So this is saying that the slopes of the tangent line to the curve would be increasing. So they would be getting greater. So in this particular graph down here, you can see this region right here is concave up. And it's because the slopes of the tangent line to the curve start off very negative. And then as our x values increase, the slopes of the tangent line to the curve get less and less and less negative until right about here, the slope of our tangent line looks to be about 0. And then as our x continues to increase, our slopes of our tangent lines keep increasing. Therefore, f prime is increasing, meaning that our second derivative has to be positive, meaning that the graph is concave upward on that given interval. Now your graph is concave downward when f prime is decreasing, or your second derivative is negative. So f prime is decreasing, that means the slopes of the tangent line to the curve are decreasing. So from our inflection point on, we see that the slopes of the tangent line to the curve start off positive, but as your x values increase, the slopes of the tangent lines that you draw to your curve continue to get less and less and less positive until right about here we get a tangent line with a slope of about 0. And then as we continue on, our slopes of our tangent lines continue to decrease. Therefore, we know that f prime has to be decreasing, meaning the second derivative has to be negative, meaning that the function is concave downward on that given interval. Now let's talk a little bit more about an inflection point, or a point of inflection. So let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at this point, c comma f of c, then this point is called a point of inflection of the graph of f when the concavity of f changes from upward to downward, or downward to upward at that point. So as you saw on the previous slide, and as you see on this one, the point of inflection or inflection point is where your graph changes from concave downward to concave upward, or concave upward to concave downward. And you could tell where that point occurs because here, the derivative of the function, or the slopes of the tangent line to the function, continue to decrease. They start off positive and they continue to decrease, and they reach 0 at about here. And then they continue to decrease, they get more and more and more negative. But then after this point, the slopes of the tangent line to the curve get less and less and less negative and get more positive and start increasing. So because f prime, the derivative of our function, the slopes of the tangent lines to the function, those slopes go from decreasing to increasing. That means that at this point, we have a point of inflection. And you will be able to find this point of inflection by setting the second derivative equal to 0. And we'll get into that later on. Now let's talk about a test for concavity. So let f be a function whose second derivative exists on an open interval I. If f double prime of x is greater than 0 for all x in I, then the graph of f is concave upward on I. If f double prime of x is less than 0 for all x in I, then the graph of f is concave downward on I. And we've already talked about this. If your second derivative is positive for all x on a given interval, then your function has to be concave upward on that given interval. If your second derivative is negative for all x values on a given interval, then you know your graph has to be concave downward on that given interval. Now let's talk a little more about points of inflection. So if c comma f of c is a point of inflection of the graph of f, then either f double prime of c equals 0 or f double prime does not exist at x is equal to c. So this should look vaguely familiar because it's similar to what we talked about when we were discussing critical numbers. Critical numbers can occur wherever the first derivative is equal to 0 or does not exist. So similarly, points of inflection can occur wherever the second derivative is equal to 0 or does not exist. So if you know that your function has a point of inflection on the graph, then you know at that point either the second derivative has to equal 0 or not exist. Now, it's important to note this distinction. If you know the second derivative of your function at a particular x value c equals 0 or does not exist at that particular x value, it does not necessarily have to have a point of inflection there. Remember, in order to be an inflection point, the graph must change from concave downward to concave upward or from concave upward to concave downward. The graph could go from concave up to concave up or concave down to concave down. That would mean that it does not have a point of inflection at that particular x value c. Because of that, it's important to make a sign chart, which is what we're going to talk about. So concave upward and downward intervals of a function. To determine where the function f is concave up or concave down, you're first going to set the second derivative equal to 0 and solve for x. These x values and any x values that cause the second derivative to be undefined are your possible points of inflection. Remember, they don't have to be points of inflection. We then are going to make a new sign chart with intervals based on your possible points of inflection and any x values where f or f prime are undefined. We then are going to pick test values in those intervals and plug them into f double prime, our second derivative. After that, you're going to look and determine if your test value produces a positive number, then the function is concave up on that interval. If your test value produces a negative number, then your function is going to be concave down on your interval. So it's basically what we did with increasing and decreasing functions, but except this time we're doing it with the second derivative, and it'll tell us whether the graph is concave up or concave down on your given intervals.
You know what my favorite dessert is? A moon pie. It's example time.
So example 1 says find the points of inflection and discuss the concavity of the graph of the function. So here's our function, x to the fourth minus 4x cubed. So the first thing we need to do here then is figure out where this function has possible points of inflection. And remember, your possible points of inflection are going to occur wherever the second derivative is equal to 0 or does not exist. So we need to find the second derivative of our function. In order to do that, we have to find the first derivative. So let's take the derivative of this function. To take the derivative of this function, we take the derivative of each term separately. Derivative over here becomes 4x to the third power. Derivative over here of negative 4x to the third, that negative 4 stays out front, so you just take the derivative of x cubed using the power rule, so it's going to be 3x squared. Then you just multiply that 3 to the negative 4 that's out here, and it becomes negative 12x squared. Now we have our first derivative, but we need our second derivative, so we take the derivative of our derivative. When we do that, we take the derivative of each term separately. Again, when we take the derivative of something with a constant being multiplied out front, you just leave that out front and take the derivative of x cubed using the power rule. So we go 3x squared, and then we multiply that 3 to the 4 that's out front, and it becomes 12x squared. Over here, this negative 12x squared, to take the derivative of that, the negative 12 stays out front by the constant multiple rule, and we just take the derivative of x squared, so it becomes 2x to the first power. Then we multiply the 2 to the negative 12. That's how you get this 24x to the first. So now we have our second derivative. And remember, possible points of inflection are going to be wherever the second derivative does not exist or equals 0. So are there any x values that would cause the second derivative to not exist? No, not in this case. So we just have to figure out wherever this second derivative equals 0. So we set it equal to 0 and we solve for x. How do we solve this for x? Well, we need to factor out a 12x from both of these terms. We then know that this times this equals 0, so we can use the zero product property and say that either 12x has to equal 0 or x minus 2 has to equal 0. We then solve each of these for x. Over here, we divide both sides by 12. We just get x is equal to 0. Over here, add 2 to both sides. We get x is equal to 2. So our two possible points of inflection are going to be at x is equal to 0 and x is equal to 2. Remember, this does not mean they are points of inflection. These are just possible points of inflection. We have to test whether they are points of inflection using our sign chart. And we're going to create a sign chart just like we did to determine where a function is increasing or decreasing with our first derivative. So in this particular sign chart, we have our intervals at the top that are going to be broken up based on our possible points of inflection. Then down here, we're going to pick test x values on those given intervals to plug into our second derivative. When we plug them in, we'll simplify, and then we'll look at the sign of whatever we get. That sign then will determine whether the function is concave up or concave down on that given interval. So first, we need to determine our intervals. Now, this function doesn't have any domain restrictions. So we are going from negative infinity to positive infinity. Now, where are we breaking it up? We're breaking it up based on our possible points of inflection, which were 0 and 2. So we're going to go from x is equal to negative infinity to x is equal to 0. And then we're going to go from x is equal to 0 to x is equal to 2. And then we're going to go from x is equal to 2 to x is equal to positive infinity. So now we need to pick test values on those given intervals to plug into our second derivative. So here on this first interval, what's an x value that we can plug in that's on this given interval? How about negative 1? So I'm going to plug in negative 1 to the second derivative for x. I'm going to simplify and I end up getting 36. Again, we don't care about the number. We care about the sign of the number. It's positive 36. Therefore, we get a positive number. Therefore, we know the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. Now let's pick a test x value on this interval. How about 1? I'm going to take 1 and plug it in the second derivative for x. I then simplify and end up getting negative 12. Again, we don't care about the number itself, we care about the sign. So the sign is negative, meaning we get a negative number. Now what does that mean? That means that the second derivative of this function on this given interval is negative, meaning that f prime of this function is decreasing on this given interval, meaning that this function on this given interval is concave downward. Now lastly, we pick a test x value on this interval. How about 3? We take 3, plug it in for x in the second derivative, we simplify, we end up getting positive 36. Again, don't care about 36, just care that it's positive. Because it's positive, that means the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. So we can answer the question by saying that the function f is concave upward on the interval from negative infinity to 0 and from 2 to infinity, and it's concave downward on the interval from 0 to 2. We can then determine if at x is equal to 0 and x is equal to 2, we have inflection points. Remember, in order to be an inflection point, the graph must change from concave downward to concave upward, or from concave upward to concave downward. It has to change. It can't go from positive to positive or negative to negative. But since at x is equal to 0, the graph goes from concave upward to concave downward, we know that there must be an inflection point at x is equal to 0. And then at x is equal to 2, the graph goes from concave downward to concave upward, meaning that there must also be an inflection point at x is equal to 2. Now, in order to figure out what the inflection points are, we need the x and the y values. So to figure out the y values, you just take those x values that we know the inflection points are at, plug them into the original function to get the y values that go with them. So if I plug in 0, I get 0. So there's an inflection point at 0, 0. If I plug in 2 to the function for x, I end up getting negative 16, meaning that there's going to be an inflection point at 2, negative 16. I can then confirm this with my graph, and I see that at 0, 0, we have an inflection point where our graph changes from concave up to concave down. And then at 2, 16, our graph changes from concave down to concave up. And then you're done. Now, example 2 says determine the open intervals on which the function is concave upward or concave downward. So to do this, we remember our steps. The first thing we have to do is figure out what our possible points of inflection are. And those possible points of inflection are going to occur wherever the second derivative is equal to 0 or does not exist. So in order to figure those out, we have to figure out the second derivative. So how do we find the second derivative? We take the derivative of this, get our first derivative, and then take the derivative of that. That'll give us our second derivative. Now, to take the derivative here, we have a function within a function, meaning that it requires the chain rule. So we're going to take the derivative of the outer function first, which is just e to that something. So that's going to be e to the something, times the derivative of that something. So times the derivative of negative x squared over 2. Now, this looks confusing, but it's actually just the same thing as negative 1/2 times x squared. So when you take the derivative of that, the negative 1/2 stays out front, and you just take the derivative of x squared, which is 2x to the first power. We then can simplify this, and we end up getting that the first derivative of our function is just negative x times e to the negative x squared over 2. Now, we need to find the second derivative, because that's what we need in order to find our possible points of inflection. So let's take the derivative of our derivative. From here, to take the derivative, we have a function times a function, meaning that this is going to require the product rule. There's a couple different ways you could do this. You could take this negative and just leave it out front until the end, do the product rule, and then multiply out the negative. Or you can just say that negative x is your first function and e to the negative x squared over 2 is your second function. Either way works. I'm going to say that negative x x is our first function, and e to the negative x squared over 2 is our second function. So to take the derivative using the product rule, I'm going to take the derivative of the first function, negative x, times the second function, e to the negative x squared over 2, plus our first function, negative x, times the derivative of the second function, e to the negative x squared over 2. We then take our derivatives. The derivative of negative x, this negative just comes out front, derivative of x is just 1, so this becomes negative 1. Over here, derivative of e to the negative x squared over 2, we already figured that out. That was negative x e to the negative x squared, so we just plugged that in there. Now we simplify, negative 1 times this just makes it negative. Over here, negative x times negative x makes it positive x squared. Now each of these terms has an e to the negative x squared that we can factor out. We then just get negative 1 plus x squared in our parentheses, which we can rewrite as x squared minus 1. Boom! We took the second derivative. Now we need to figure out what our possible points of inflection are. Remember, those are any x values that cause the second derivative to either not exist or equal 0. Are there any x values we can plug in here that would make this not exist? No. So all we have to worry about is setting it equal to 0 and solving for x, figuring out what x values cause this second derivative to equal 0. So how do I set this equal to 0? Well, first thing I want to do is take this x squared minus 1, and I'm going to factor that out. What is x squared minus 1? That's a difference of squares. So when I factor that, it's the same thing as the quantity x minus 1 times the quantity x plus 1. Now I have this times this times this is equal to 0. So by the zero product property, I can set each of those things equal to 0 and solve for x separately. So how do I solve this for x? Well, I need to get rid of this e. So I'm going to take the ln of both sides. Now ln of 0, that doesn't exist. So we can't solve for x here. Let's go over here. We're going to add 1 to both sides. We get x is equal to 1. Here we subtract 1 from both sides. We get x is equal to negative 1. So our only possible points of inflection are going to occur at x is equal to 1 and negative 1. So in order to figure out which intervals the function is concave upward or concave downward on, we're going to create our sign chart based on these possible points of inflection. Remember, we got our intervals, we got the test values that we're going to plug into the second derivative, figure out the sign of those test values, and those signs will then tell us whether the function is concave upward or downward on those given intervals. So our possible points of inflection are going to occur at x is equal to negative 1 and x is equal to positive 1. So when we make our intervals, here there is no domain restriction, so we're going from negative infinity to positive infinity. So we're going to start at negative infinity, and then we go to our first possible point of inflection, which is going to occur at x is equal to negative 1. So negative infinity to negative 1, then from negative 1 to positive 1, and then after that from positive 1 to infinity. Now that we have our intervals, we can pick test x values on those given intervals to plug into our second derivative and look at the sign of those. Test x value on this given interval that we can plug into our second derivative. How about negative 2? If I plug in negative 2 to the second derivative and simplify, I end up getting e to the negative second times 3. Now e to the negative second is just 1 over e squared. That's a positive number. Times 3, still positive, meaning that the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. Now let's pick a test x value on this interval. How about 0? I plug in 0 to the second derivative and I simplify, and I end up getting e to the 0, which is 1 times negative 1, which is negative 1. So this is negative, meaning that the second derivative of this function on this given interval is negative, meaning that f prime of this function on this given interval is decreasing, meaning that this function on this given interval is concave downward. Lastly, we pick a test x value on this interval to plug into our second derivative. How about 2? We plug in 2 and we simplify. We end up getting e to the negative second times 3 again. Remember, e to the negative second, that's just 1 over e squared, which is still positive. Times 3, still positive. So the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. So we can answer our question by saying that the function f is concave upward on the intervals negative infinity to negative 1 and 1 to infinity, and it's concave downward on the interval from negative 1 to positive 1. Now I know this doesn't ask, but since the function goes from concave upward to concave downward at x is equal to negative 1, there's going to be an inflection point at x is equal to negative 1. And then since the graph goes from concave downward to concave upward at x is equal to positive 1, there's also going to be an inflection point at x is equal to positive 1. And you can confirm this with your graphing calculator. You see that at x is equal to negative 1, the function goes from concave upward to concave downward. So there's an inflection point at x is equal to negative 1. At x is equal to positive 1, the graph goes from concave downward to concave upward. So there's also an inflection point at x is equal to positive 1.
I gotta rescue Matthew McConaughey from this black hole. You try.
Okay, doing the same thing here. So we want to determine the open intervals on which the function is concave upward or concave downward. To do that, we need to figure out what the possible points of inflection are. Now remember, possible points of inflection occur wherever the second derivative is equal to 0 or doesn't exist. So we need to figure out the second derivative of this function. So to do that, we have to take the derivative of the first derivative. So let's take the first derivative first. To take the derivative of this function, we have a function being divided by another function. So to take the derivative of this quotient, we have to use the quotient rule, which says we take the derivative of the numerator, multiply it to the denominator, then subtract the numerator times the derivative of the denominator all over the denominator squared. Now let's take the derivative of each part of this. The derivative of x squared plus 1 is just going to be 2x to the first plus 0. Over here, derivative of x squared minus 4 is going to be 2x to the first minus 0. We then simplify those, and we can distribute here the 2x to the x squared and to the negative 4. Over here, we can distribute the 2x to the x squared and the positive 1. We then combine like terms, and we get negative 10x over x squared minus 4, the quantity squared. Now this is our first derivative. We need the second derivative to figure out our possible points of inflection. So we need to take the derivative of this. To take the derivative of this, we have a function being divided by another function. So this again requires the quotient rule. So I'm going to take the derivative of the numerator, multiply it to the denominator, minus the numerator times the derivative of the denominator all over the denominator squared. Over here, the derivative of negative 10x, the negative 10 pops out front by the constant multiple rule. We just take the derivative of x, which is just going to be 1. So it's going to be 1 times negative 10. Over here, derivative of x squared minus 4, the quantity squared. This is going to require the chain rule. So we take the derivative of the outer function first. It's going to be 2x squared minus 4 to the first power times the derivative of our inner function, the derivative of x squared minus 4, which is going to be 2x minus 0, which is just 2x. Now, before I simplify all this term over here and this whole term over here both have an x squared minus 4, which I can factor out. Now, why do I do that? Because there's x squared minus 4 to the fourth power in our denominator. So I can actually cancel this out with one of these down here, leaving x squared minus 4 to the third power in our denominator. We then simplify the rest of our numerator, and I can take negative 10x squared, add it to 40x squared, and I end up getting positive 30x squared. Last thing I can do is factor out a 10 from the numerator, and it looks like this is as good as it's going to get. Here's our second derivative. Now again, to find the possible inflection points, I need to figure out where does my second derivative either not exist or equal 0. Well, what values of x would cause this to equal 0? Those would be any x values that cause the numerator to equal 0. So if I were to set that equal to 0 and solve for x, I would get 3x squared is equal to negative 4. No, there's no way to get x squared to equal a negative number. Therefore, you could say that there's no x values that could cause this to equal 0. But are there any x values that would cause the second derivative to not exist? Yeah, x is equal to 2 and negative 2 would cause the denominator to equal 0, meaning that the second derivative would not exist. Now, why is that? Well, if you look at the original function, if I plug in 2 for x or negative 2 for x, that causes the denominator to equal 0 in the original function. And that means that there's going to be vertical asymptotes at x is equal to 2 and negative 2. Now, what does that mean for your sign chart? Well, when you're creating a sign chart, you're still going to break it up based on whatever x values cause the second derivative to either equal 0 or not exist. Even though there's asymptotes here, we're going to use negative 2 and positive 2 to break up our sign chart. Since there's no restrictions for our domain besides the asymptotes, we're going to go from negative infinity to positive infinity and break it up based on our asymptotes. So for our first interval, we're going to go from negative infinity to negative 2. For our second interval, we're going to go from negative 2 to positive 2. And then for our last interval, we're going to go from 2 to positive infinity. Now we're going to pick test x values on each of those intervals to plug into our second derivative. Then we can look at the sign of those and figure out whether the graph of our function is concave upward or downward on those given intervals. So for our first interval, we're going to pick a test x value to plug in. How about negative 3? Take negative 3, plug it in the second derivative for x, and I simplify. I end up getting 310 over 5 cubed, which we know is going to be a positive number, meaning that the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave up. Next, we pick a test x value on this interval. How about 0? When I plug in 0 to the second derivative for x and I simplify, I end up getting 40 over negative 4 cubed. Now, since it's negative 4 cubed, it's going to stay negative, meaning that this is going to be negative, meaning that the second derivative of this function on this given interval is negative, meaning that f prime of this function on this given interval is decreasing, meaning that this function on this given interval is concave down. Lastly, we pick a test x value on this given interval to plug into our second derivative. How about 3? So when I plug in 3 to the second derivative for x and simplify, I end up getting 310 over 5 cubed again, which we know is positive, meaning that the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is going to be concave up. We can formally answer the question by saying the function f is concave upward on the intervals from negative infinity to negative 2 and 2 to infinity, and concave downward on the interval from negative 2 to 2. We can then confirm this with our graphing calculator, and you can see that the function is concave upward on the interval from negative infinity to negative 2. Then at x is equal to negative 2, we have our asymptote. Then after that, from negative 2 to positive 2, the graph is concave downward. Then at x is equal to 2, we have another vertical asymptote. Then from negative 2 to infinity, we can see that the graph is concave upward again. Now let's quickly talk about the second derivative test that says let f be a function such that f prime of c is equal to 0, and the second derivative of f exists on an open interval containing c. If f double prime of c is greater than 0, then f has a relative minimum at f of c. If f double prime of c is less than 0, then f has a relative maximum at f of c. Lastly, if f double prime of c is equal to 0, then the test fails. That is, f may have a relative maximum, minimum, or neither. In such cases, refer back to the first derivative test. So if you recall, the first derivative test has you find critical numbers, and then you have to determine if the function goes from increasing to decreasing or decreasing to increasing at that critical number. If it goes from increasing to decreasing, you have a relative max. If it goes from decreasing to increasing, you have a relative min at that critical number. Here, for the second derivative test, what it wants you to do is figure out your critical number, x is equal to c. That's where the first derivative equals 0. So if you have a critical number at x is equal to c, you're going to take that critical number, c, and plug it into the second derivative. If you get a positive number, that means the graph is concave upward on that given interval. And because it's concave upward, you're going to have a relative minimum at that critical number. If you plug in your critical number to your second derivative, you get a negative number. That means your graph is concave downward on that given interval. Because it's concave downward, you're going to have a relative max at that critical number. And then if it equals 0, then you just have to refer to your first derivative test that we just talked about. Now, example 3 says find all relative extrema. Use the second derivative test when applicable. To find all relative extrema, we're going to use the second derivative test. How do we do that? Well, we need to find our critical numbers and plug them into our second derivative. First, we are going to find our critical numbers. How do we find our critical numbers? It's anywhere where the first derivative is either equal to 0 or does not exist. So, first thing we need to do is find our first derivative. Let's take the derivative of this function. I take the derivative of each term separately. Here, the negative 3 pops out front. I then just take the derivative of x to the 5th, which is 5x to the 4th power. Over here, same thing. The 5 pops out front. I just take the derivative of x cubed, which is 3x squared. Multiply the 5 and 3, multiply the negative 3 and the 5. Boom, got my first derivative. Now, is there any x value that would cause this to not exist? No. So for our critical numbers, we just have to worry about whatever x values cause this to equal 0. So we set it equal to 0 and we solve for x. How do we do that? Well, I can actually factor out a negative 15 and an x squared from each of those terms and end up getting negative 15x squared times the quantity x squared minus 1. Now, if you recall, this is a difference of squares, which factors into x plus 1 times x minus 1. Now we have three things multiplied together that equal 0. By the zero product property, I can set each of those things equal to 0 and solve for x. Over here, I divide both sides by negative 15 and then square root both sides, I get x is equal to 0. Over here, I add 1 to both sides, I get x is equal to 1. Here, I subtract 1 from both sides, I get x is equal to negative 1. So my three critical numbers, my possible max and min values, are going to be at x is equal to 0, x is equal to 1, and x is equal to negative 1. So after that, again, I'm using the second derivative test, which means I need to find my second derivative. So I just take the derivative of my first derivative, which means I take the derivative of each term separately. Here, when I take the derivative, the negative 15 pops out front. I just take the derivative of x to the 4th, which is 4x to the 3rd power. Multiply the 4 and the negative 15, I get negative 60. Over here, take the derivative of 15x squared. The 15 pops out front. Derivative of x squared is just going to be 2x to the 1st power. 2 times the 15 gives you that 30. Now that I've found my second derivative, what I can do is I can start the second derivative test. So I'm going to take the critical numbers and plug them into the second derivative. What are my critical numbers? They are negative 1, 0, and 1. I plug each of those into the second derivative. Let's start with x is equal to negative 1. When I plug that into my second derivative and I simplify, I end up getting positive 30. Because it's positive, that means that at this x value, at this critical number, this function is concave upward, meaning that at x is equal to negative 1, this function is going to have a relative minimum. We then plug in 0 to our second derivative. When we do that, we end up getting 0. Now, what happens when it equals 0? That just means the test fails. We don't know whether it's going to be a relative max or min, which means we have to use the first derivative test. That says that we have to determine on either side of x is equal to 0, does the function go from increasing to decreasing, decreasing to increasing, or neither? If you actually do it out, you see that the first derivative goes from positive to positive, meaning that the function goes from increasing to increasing, meaning that there's neither a relative max nor a relative min at x is equal to 0. We then move on to x is equal to 1. We plug in 1 to our second derivative, and we end up getting a negative number. Because it's negative at x is equal to 1, that means that this function at this critical number is concave downward, meaning that at x is equal to 1, this function is going to have a relative maximum. We can then figure out what those max and min values are by plugging in our critical numbers to the original function. So we take -1, plug in the original function for x, we simplify, we get -2. That means that this function is going to have a relative minimum of -2. We then figure out what our relative maximum value is by taking 1, plugging in the original function for x, simplifying, we end up getting 2. Therefore, this function is going to have a relative max of 2. We can confirm this with our graphing calculator, and you see that your function does have a relative minimum value at 2, -2. It also has a relative maximum value at 2, +2. And you can see that at x is equal to 0, we have neither because the function goes from increasing to increasing.